How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And my program today I entitle Some Miscellaneous and Wondrous Adventures in the Subject of Heat. Now, before I leave it, here is an interesting inquiry for you to pursue. I mentioned on an earlier occasion the behavior of this little radiometer, known as a Crookes radiometer. And I said that the way it's devised and designed and the way it works is that the black faces always retreat from the observer. Question, what would this do if placed between two cakes of ice? Supposing I placed it between two cakes of ice, what would it do? That's a very good question. But let me go on with my adventures. Here I have a large tin can in which I've put some water, and I have boiled the water for a while and driven out all the air and the occluded gases in the water. And now I'm going to, and you see that because the steam here, which is condensed water vapor, now I'm going to take this away from the burner, and I'm going to stopper it up, and I'm going to shut off my gas here. And I invite you to listen. Oh, listen, listen, listen. Oh, man, something is happening. Now, you know all about this. The water vapor inside is condensing into the water liquid state. The pressure in the can is getting less, and the atmosphere is beginning to do its oh, there it is. But I don't want to wait all week for it. I'll just hasten the process. Watch it. Oh, watch it. There it is. Uh-oh. There it is. It got me on this side a little bit, but that's all right. This is an experiment in physics. Isn't that incredible to witness? Fantastic. Now, more about this. Supposing I tried to take out that stopper. Supposing I tried to take out that stopper. Answer, it is very difficult to get out. Why? Because the pressure in the can is vastly less than atmospheric. But there it is. I'm going to do something stranger still. I'm going to pour some more cold water on there. No, I was hoping to hear the water in there boil again, reducing the pressure. I think I can do that. I want to do that. Yeah, I hear the water boiling. Yeah. But let me go on with my business. Miscellaneous adventures. Here I have a cake of dry ice. Now, you know what dry ice is. Solid carbon dioxide. Solid CO2, a gas made solid. Has very strange properties. It sublimes. That is, it disappears without ever going into the liquid state, like camphor. Like camphor. Here I have a silver coin, a silver dollar. I'm going to lodge it in here and watch. I am melting some of that. Watch it. Oh, a little troublesome. There we are. Come on. I'm having a little trouble with it. I want to warm this coin up. Notice conduction. The heat of my hand going into the coin. I'll try it once more. There we are. Listen. Yeah, this is to be likened to a thing in the history of physics known as a Trevelyan rocker, which a Britisher of long ago designed. And I invite you to go look into it. Trevelyan rocker. Now, look at that. I want to know why it's doing that. Look at that. And I'm going to tell you why it's doing it, because you know I'm kind-hearted. It makes contact on one side with the dry ice. The other side is left free. Heat energy is taken away. Gases arise. push it over. I haven't said everything, but that's enough for you to think about. Miscellaneous further adventure. Question. I want to cook a hamburger very fast. Question. Should I put the ground meat in a skillet, turn up the burners high, and cook it very fast to cook it fast? No. Answer no. Why? Here I have cooked a hamburger very fast, and it is all brown and black and scorched on the outside, but it is not cooked inside. Why? It is not cooked inside because carbon is a good insulator, and the meat didn't get cooked inside. So here is a hamburger that I have cooked very gently and slowly, and it is cooked entirely through and through. So, paradox. In order to cook a hamburger fast, you cook it slow. And I think that's wonderful. Next miscellaneous adventure. Housewives, teachers, people who sometimes prepare onions find that it makes them cry. The vapor pressure is very high. That's why you cry. Notice, vapor pressure very high. That's why you cry. I'm a poet and don't know it. Question. How can I make ready an onion so that when I peel it and slice it and dice it, I don't cry? Answer. Put it in the refrigerator, in the freezing unit for a little while, and lower its temperature very substantially, as I have done with this one. It's a little hard to cut, but I smell nothing. Why? I have lowered the vapor pressure. Now, another discussion. Viscosity. Another interesting thing. Viscosity. V-I-S-C-O-S-I-T-Y. Viscosity. What do we mean by viscosity? We mean the freedom with which something flows. So you put crankcase oil in the crankcase of your car, and when it's cold, it does not flow so freely. When it gets warmer, it flows more freely. So in the case of liquids generally, the viscosity goes down the higher the temperature. And I have an interesting little tale to tell. Here is some molasses in this vessel. It is at room temperature. If I should pour it, it would pour so fast. Now here is some that I have cooled, chilled in the refrigerator. And clearly it would pour at a lesser rate, very much more slowly. So I have to tell you a story. When I was a little boy, my mother used to make cornbread, Johnny cake, using molasses. And she had a recipe all in her head, and the recipe called for the following. In the summer, the recipe called for 3 glubs. You got it? She turned over the jug and it went glub, glub, glub. And that was enough for the recipe. But in the winter, there was a different number of glubs. And I could never understand that when I was a little guy until I learned what we mean by viscosity and how it behaves with change in temperature. Question, did my mother have more glubs in the winter or less glubs in the recipe for her Johnny cake? I think that's a wonderful, good question. Next demonstration, strange one. Wonderful, miscellaneous adventures. Here I have a beaker, and here a hollow sphere in which I have some lead shot. So, this experiment has to be virtual, and it is a wonderful thing to witness. Watch me. We will imagine that I have some water in this beaker. Now, this sphere is so designed that if I put it in warm water, it sinks, and if I put it in cold water, it floats. That is warm water at room temperature, say, and cold water, that is ice water as you would drink water and ice. Now, here is a wonderful thing to do. Supposing I put this in a vessel of warm water and it sinks to the bottom, just as we have it here. Now what could I do? I could add some ice. Add ice. You see, this experiment, ladies and gentlemen, is a virtual one, and you will imagine it. I add ice, and lo and behold, like a mystic business, up comes the sphere, because as the water cools, it gets more dense. On the other hand, supposing I put it in a vessel of ice and water of such composition and temperature that it just floated. Here it is just floating. Here it is just floating. Now, if I left it here in the studio, as time goes, would not the temperature of the water rise? Would not the water get less dense? And what would this do? Creep down ever so slowly. A very mystic adventure regarding the floating and sinking of a hollow sphere. So you see, people, how I entitle things. The mystic adventure, because it is something to think about, which is not generally in the books. Next demonstration, wonderful thing. I spoke about the viscosity of liquids. The viscosity of liquids goes down with higher temperature. That is, the oil in your crankcase flows more freely, the hotter the system. But how about the viscosity of gases? The viscosity of gases. The viscosity of gases. It is a remarkable thing that the viscosity of gases increases with rise in temperature. And I have a demonstration which we will imagine. Here is a T-tube, unsymmetric. This arm is short and this one is long, and it's connected to a burner. And here's what I would do. There is the tube with unequal arms, and I put gas in here, and I light the ends of the tube which are turned upwards. I light the ends of the tube. The first thing we witness is this. This flame here would not be as high as this flame there. That's the first thing to observe, and that's very important. Why would we see that? Well, answer. The drop in this line is much greater than the drop in this line, so this is getting less gas than that. Now remember what I want to do. I want to show that the viscosity increases with temperature. So, with these two flames, this one low, that one high, I now play another flame on this pipe. This is a tube. I used to say a hollow tube, but it's a tube. You know, a tube's got a hole inside. Question. When I heat this, what happens? This flame goes out. And that's a remarkable thing, because obviously when we heat the tube, the bore gets bigger, so more gas should come here. But more gas does not come here. It flows more sluggishly with the higher temperature. So it is a most uncommon thing to discover that although the viscosity of liquids goes down with rise in temperature, the viscosity of gases goes up. And now, once more, with my oscillating coin. There it is. There it is. And I think that's wonderful to see. I urge you, whenever you handle dry ice, CO2, be very careful. 95 degrees below 0 centigrade, enough to severely freeze you. And I thank you for listening.